There are a couple of different forms of Fourier series and a couple of different ways to write them down. So let's get them straight. So first off, there's the notion of a generalized Fourier series, which is basically just an expansion with respect to an orthonormal basis in an inner product space. So for any element of an inner product space V, if we have an orthogonal system, like so a sequence of orthogonal vectors Vn, and F is given by the sum of Cn Vn as n runs from 1 to infinity, then it will necessarily be the case that those Cn's are the lengths of the projection of F onto each of the corresponding Vn basis vectors. And so that's given by the inner product of F against Vn over the inner product of Vn against Vn. And so it's worth noting also, so we can note here that if you look at the inner product of F against Vn over Vn against Vn, that denominator there, that's actually the same thing as norm Vn quantity squared. And so the nth component of F is written like this. So this is the full projection onto Vn of F, right? It's a scalar multiple of Vn where you've multiplied by this scalar right here. But we can also rewrite it by splitting that squared term in the denominator. We can rewrite this as the inner product of F against Vn over norm Vn times Vn over norm Vn, in like that. And then if we relabel this renormalized vector as u, then this is F against un times un. And then if you have divided a vector by its magnitude, like this, then you get a unit vector. So just to see that, in fact, u is a unit vector, we can check by taking the magnitude. And if you take the magnitude of un, this is going to be the magnitude of Vn over magnitude Vn. And then since that's a scalar multiple, we can take this scalar multiple here, which I will circle in blue, and we can pull it out in front of the magnitude bars, where it comes out like that, and all it leaves behind inside is just the Vn, and then that's definitely equal to 1. So you can see that this guy is definitely a unit vector. So that would make it an orthonormal basis if you use the u's instead of the v's. Okay, so carrying on, we then have the classical Fourier series. So now this is F in L2 of the interval from, oh, and you know what? I messed up there. I actually meant for that to be of a general length, minus L to L. So let me replace that. Then the orthogonal system that we use is the constant vector, which will normalize as 1/2, so the constant function 1/2, and then the cosine n pi x over L's and the sine n pi x over L's. Those will all be orthogonal on our symmetric interval. And then F will be equal to a naught over 2 plus the sum of an cosine n pi x over L plus bn sine n pi x over L. And it's worth pointing out here that this equal sign right here is in the mean squared sense, or in other words, the convergence of that series is in the sense of L2. And then, of course, those coefficients are given by the standard formula for the Fourier coefficients on the interval from minus L to L. Okay, then there's also the exponential form. And so this is going to be for F in L2 of minus pi to pi. And we will use as our orthogonal system e to the I n x, now where n is allowed to be any integer, positive or negative. And these things form an orthonormal basis for this space here. And so if you look at e to the I, well actually here, let's just leave the n's out of it. E to the I theta, that's by Euler's formula, cosine theta plus I sine theta. And so if we look at e to the minus I theta, then since cosine is an even function, we just get cosine theta. And since sine is an odd function, we get minus I sine theta. And so this is actually, you can consider it as a 2x2 linear system, right? And so if you solve for what cosine and sine are, we see that cosine theta is going to be e to the I theta plus e to the minus I theta over 2. And sine theta is going to be e to the I theta minus e to the negative I theta over 2I. And so that means then that if we look at an cosine n theta plus bn sine n theta, this is going to be, and let's do some messing around with formulas. So we have an e to the in theta plus an e to the minus in theta, and each of these is over 2. And we have bn e to the in theta over 2I minus bn e to the minus in theta over 2I. Then let's see, so I can grab these guys and duplicate, because the only thing that I need to change here is I'm going to move the i's into the numerator, and 1 over I is the same thing as minus I, so I have to pay for it with that for a minus, with a minus sign. And then I use the fact that well, I just gathered them together. So then we have an minus I bn over 2 as my coefficient of e to the in theta, and an plus I bn over 2 e to the minus in theta. So I've converted now my an and bn's from coefficients of sine and cosine into being coefficients for the positive and negative exponential. And so if I look at theta equal to pi x over L, then my Fourier series is going to look like a naught over 2 plus, and then I have the sum n equals 1 to infinity of an minus I bn over 2 e to the in theta, and sum 1 to infinity coming from the sine portion, which is this guy, or actually I shouldn't call that the sine portion, the negative in theta part, right? And so now I can manipulate this further as well. So what am I going to do? Let's see. I'm going to reindex this second one so that it goes from minus 1 to minus infinity. And then in that case, the subscripts are going to be minus n, and the last one becomes positive n. Okay, so now I have nothing but terms in e to the in theta, and in fact this one over here, this is e to the I0 theta. So I can begin to collect all these together. I just need to notice that when it comes to the an's, a sub minus n is the same thing as an, because those coefficients come from, so I'll just make that correction there, come from cosines. And meanwhile, the b sub minus n, maybe I should write this. So a sub minus n is equal to an, and b sub minus n is equal to minus bn, because it comes from the sine functions, and those are odd. So let me make that correction there. And then all of a sudden, you see that these critters now match, and we can string everything together, and we have the sum over, and now n runs through all integers, so from minus infinity to positive infinity, including 0. And it's Cn e to the in theta, where Cn is an minus I bn over 2, which is the same as 1 over 2 times the integral from minus L, 1 over 2L times the integral from minus L to L of fx e to the minus inx over L dx, which is 1 over 2L integral from minus L to L of e to the inx over L conjugate times f of x dx, which means that this is e to the inx over L against f in the complex inner product, where the first one gets a conjugate. And so if that part with the conjugate looks like funny business to you, just remember that when we look at unit complex numbers, okay, well that was a little off kilter. There we go. If this is theta, then this is minus theta, and this point here is e to the I theta, and this point here going in the opposite direction is e to the minus I theta. But you can see I get to the same point as if I had just reflected across the x-axis, which is the geometric version of taking the conjugate. So those things are the same. Okay, and so from this you can see then that the magnitude of f squared is then going to be the sum over the integers of the absolute value of the coefficients squared, where the coefficients Cn are given by this formula we just saw. And so this is once again Parseval identity, just the exponential form of it. So again, that's the same thing as the complex exponential form of Pythagoras' theorem.